Okay, welcome. We're gonna get started in a minute. You have 15 minutes to present. I'll give you a 5-minute, a 2-minute, and a 1-minute warning, so just keep an eye on my markers. We ask that you begin by just each introducing yourselves, and then once you're done, begin whenever you're ready, and I'll start the timer.
Okay, thank you.
Thanks.
So, all right. Welcome, judges, competitors, and guests. My name is Jessica Young.
I'm Grace Law.
I'm Stephen Gu.
I'm Brandon Willoughby.
I'm Brandon Yang, and to make it simple, we're all seniors.
And we are from the North Carolina School of Science and Math, and we are presenting on the hot button issue, staying cool as the world heats up. Heat waves are deadly, but unequally deadly. Heat waves have devastating impacts on people's mental and physical health and could lead to death. In fact, according to the EPA, over 1,300 people every year in the United States die due to heat-related reasons. And these numbers will continue to rise as temperatures rise. Within these numbers, we found that certain communities are disproportionately affected. Thus, the equitable distribution of funds could save countless lives. So for our first model, we wanted to know how temperature changes within a house without AC for the first 24 hours to determine which kinds of houses are most susceptible to heat waves. So we have three major assumptions. Number one, the initial starting temperature is 78 degrees Fahrenheit. We got this from the Memphis Light, Gas, and Water Division on the most energy efficient temperature. Second, all units are rectangular for simplicity, and the number of rooms inside a unit is irrelevant since the system is a house, and thus whatever's happening inside the house isn't too important. And third, the proportions of households before 1950s is negligible. This is because the MathWorks data given to us is from 1950s to present day 2024. And speaking of data, we have four major points that we care about, which is number of stories, units and structures, size of unit, and then the year the house was built.
So we're also given data on what the temperatures are in Memphis during a 24-hour period during a heat wave. And our team decided to use Newton's law of heating and cooling to determine the temperature inside of a house during these 24 hours. But first, we have to find the heating and cooling constant K, which depends on 5 main parameters, 2 of which are thermal conductivity and specific heat capacity, which both depend on the house material. Our team wasn't able to find enough information on how house materials changed from 1950 until the present. So, except we knew that houses were mainly made out of brick in the past and now are made out of wood. So we made the assumption that in 1950, houses are made entirely of brick, and in the present, houses are made entirely of wood. And as time increases, the percentage of the house made of brick decreases linearly. We're also interested in A, which stands for the exposed surface area, as well as M, the mass of the house, and D, which represents the thickness of the exterior walls, which we're assuming is going to be 0.2 meters. So using our linear gradient concept, we come up with the 2 formulas in the top for thermal conductivity and specific heat capacity. As for the exposed surface area, that's equal to the number of exposed sides E multiplied by the dimension of each unit, which is L. And then finally, for the mass of the house, that's equal to the density of air multiplied by the volume of the house, where volume is just the height, which we're assuming is going to be 9 feet, multiplied by the dimension of the unit, which is L. So now, using these the four inputs that Jessica talked about, our model will output graphs showing indoor temperature, which are the blue dots, versus outdoor temperature, which are the orange dots. And we decided to show this for 5 full days because the indoor temperature doesn't equilibrate to the outdoor temperature in just 24 hours. And as you can see, we're mainly concerned with the rate at which the indoor temperature equilibrates to the outdoor temperature because that's what sets these 4 graphs apart, which show the temperatures for houses 1 through 4. So now I'm going to conduct a sensitivity analysis. On the left is the graph showing indoor versus outdoor temperature for house 1. And on the right, we're changing each of the 4 input parameters slightly to see how the blue curve, which is the indoor temperature, changes. As you can see, our model is very robust when it comes to increasing and decreasing the dimension of the unit, which is shown in the top left. top right. And then that's because the blue curve doesn't change much. Our model also shows that houses that are built later are much better at insulating because the temperatures decrease drastically, and also there's less variability in the temperature, and that's shown in the bottom right. The main strength of our model is that we have visual graphs, so it's easy to compare indoor versus outdoor temperature, and we're also showing this for 5 whole days, so you can understand the relationship between those temperature values. And however, the main weakness of our model is the linear gradient concept. Obviously, building practices change discretely, and we tried to model this continuously, and so that was the best we could do. And we're also not sure if the M in our formula stood for the mass of the air, the mass of the house, or both, so we just assumed it was the mass of air.
So moving on, with heat waves also comes an increase in AC usage, which can often lead to the power grid overloading. So that's why in part 2, we're going to model the peak energy demand in Memphis for the summer months and how this might change in 20 years from now. So we began by assuming that our selected sectors encompass all electricity consumption, meaning that no other sectors contribute. Secondly, we assume that no unpredictable factors such as sudden economic policy change or natural disasters affect our regression models because they're simply too unpredictable. And thirdly, we made the assumption that Memphis's peak energy demand can be modeled as a proportion of Tennessee's peak energy demand. While this might leave certain sectors like residential underrepresented because Memphis is an urban area, we did not have enough data regarding Memphis specifically to reliably do our model. So we began by splitting demand into 2 parts, demand from cooling and demand not from cooling. So demand from cooling is a function of temperature, which itself is a function of time. And the demand not from cooling is a sum of each sector's energy times a constant K that represents how much is not used for cooling. So here are our regressions for each sector. As you can see, we use logarithmic for residential and commercial, which kind of shows a slowing growth rate in accordance with Memphis's slowing population growth. We used a bell curve for the industrial sector to kind of capture an upward and downward trend while still maintaining a horizontal asymptotic floor behavior so that it doesn't go negative. As you can see, the decrease in industrial will be so, later on we'll see that the decrease in industrial will be so great that despite the increase in the other sector's energy consumption, the total energy will decrease for Memphis in 20 years. So to determine temperature as a function of time, we've had a sinusoidal regression to local Memphis weather data, and then we also tried to add a linear component to account for climate change, but it was not very significant.
So next, we need to predict cooling, energy consumption from cooling, and we found this to be a proportion times the total peak demand. And we found this constant by dividing the total electricity consumption for cooling in Tennessee by the total electricity consumption in Tennessee. So next, we ran a regression to determine energy consumption from cooling as a function of temperature. And we found this to be, we chose a quadratic regression because we thought that at moderate temperatures that the energy consumption from cooling would be lower, and as you increase or decrease temperature, that the energy consumption would increase. And after this, we plugged in our temperature regression from earlier to get energy consumption from cooling as a function of time. So next, we projected results in 2025 and in 2045, and we found that there was about a 10,000 megawatt hour decrease in the peak demand, which can be primarily attributed to the decrease, our projected decrease in the industrial sector. And this suggests that if Memphis is currently able to handle peak demands, that will likely be able to handle peak demands in the upcoming year. So next, we ran a sensitivity analysis by varying temperature from 82 degrees Fahrenheit to 94 degrees Fahrenheit. We found that for every 1 degree increase in temperature, there's about a 2% increase in the energy used for cooling. Our main strength of our model is that we took into account each sector separately and ran independent regressions on those. And all of our data was, almost all of our data was sourced from the EIA, which ensures consistency in our data. But the primary weakness was the over-reliance on regressions, and our temperature regression was quite crude, and it's quite hard to predict peak temperatures, especially 20 years in the future.
All right, and part 3 asks us to beat the heat. Our goal is to develop a quantitative vulnerability score to determine the most at-risk neighborhoods and develop a funding allocation plan to help those at-risk communities. So our team created the vulnerability score V for all 27 of Memphis's neighborhoods. Note that this score is on the range from 0 to 1, where 0 represents a community that is not at risk, and 1 represents the community that is the most at risk. Our team ultimately decided that only 5 parameters would play into determining the vulnerability of the community. The first one is the average income of all working residents. We'll call that I, and that's an inverse relationship to V, because if the community is generally more affluent, then they can invest in more quality HVAC systems. The next is the dependency ratio E, which in a human geography sense is the people over 65 and under 18 over the total population, so the elderly and the children. And that's a direct relationship because while everyone is vulnerable to heat waves, the elderly and children are especially vulnerable. So that drives up the vulnerability of the community. The third is the percent of adults with cars. We'll call that C, and that's also an inverse relationship because if more adults have access to cars, then they can get away from the heat waves if needed. The fourth is the average age of the house. We'll call that Y. Note that this is calculated by 2024 minus the year that the house was built. And as we've shown in Model 1, that's a direct relationship because older houses tend to have more poor insulation, which lets in more heat. The last one, which we'll directly use Model 1 for, is the average temperature in the house. We'll call that T. And keep in mind that that is the acute period when power grids are down and there is no HVAC system in the house. And that's a direct relationship. So with all 5 of these parameters considered, we have the formula in the bottom left. And the last step involves using min-max normalization to normalize the scores. The largest value for V we get, we set to be 1, and the smallest value of V we get, we set to be 0.
So I'm going to quickly revisit Model 1 because we're going to use that Model 3. So in Model 1, we had 4 inputs: the year that the house is built, the number of units in the house, the number of stories in the house, and the dimension of each unit. And then our model spit out a graph showing indoor versus outdoor temperature during the first 5 days of the heat wave. So we can find the average temperature in that house by just taking the average of those blue dots, and we're going to use that to help us with Model 3. But first, we have to make a few assumptions about these house types. We're going to assume that a detached home is made of 1 unit, 2 stories, and has a size of 200 square meters, and make similar assumptions for the other 3 house types. Now we're ready to calculate the average temperature of a house in a given neighborhood, and I'm going to do a sample calculation for South Memphis. So the first step is to find the average year that a house is built in that given neighborhood. And for South Memphis, that's 1957, and we can find that by just easily manipulating the data given to us. The second step is to find the average temperature given a certain house type in South Memphis. There's 4 house types, and we're going to use Model 1 to calculate the average temperature by plugging in the year 1957 and the 3 values that we made assumptions about on the previous slide. The final step is to find the average temperature given any house type in South Memphis, and that's going to be a weighted average of our 4 temperature values depending on how many houses in South Memphis are detached homes versus townhouses, etc. So you can see that the average temperature of any house in South Memphis is going to be 88.7 degrees Fahrenheit. Now we're able to create vulnerability scores for each of the 27 neighborhoods in Memphis, and as you can see, South Memphis is the most vulnerable neighborhood with a score of 1. As for the funding plan, it's actually quite simple. Our team decided to allocate funding proportionally with the vulnerability score. So let's assume that Memphis has $10 million to spend in funding. Well, then South Memphis would receive $10 million times their vulnerability score 1 divided by the sum of all the vulnerability scores, which is 8.038, which comes out to be $1.2 million. As for Piperton, which was the least vulnerable neighborhood according to our model, they get $0 because their score was 0. The main strength of our model are the normalized vulnerability scores and also how we use Model 1. As for the weaknesses, we weighted all of the parameters the same in our vulnerability score formula, and that's because we tried to do some scalar weighting, but that just went away after we normalized. Okay, I'm going to quickly summarize our entire project. So in Model 1, we used Newton's law of heating and cooling to create graphs showing indoor versus outdoor temperature for 5 full days. In Model 2, we split up energy demand by sector and ran regressions on each of those independently. And then in Model 3, we created a normalized vulnerability score using Model 1 and then created a funding plan accordingly. As you can see, Model 2 was more informative for government officials, while Model 1 was more useful in helping us create Model 3. We would like to thank MathWorks and SciEM for giving us this amazing opportunity to compete, and thanks so much for listening.
Okay, my question is about your part one, specifically about those 5 days, how the temperatures go up and never go down. Does it change the model in the long run? And what are your justification for 5 days explicitly?
Okay, hold on, let me just go to that slide. So we showed it for 5 full days because we thought that just showing 1 day didn't do the model justice. It didn't show how, like when the indoor temperature will equilibrate to the outdoor temperature. And because what we're more concerned about is the rate at which that equilibration like occurs, because we want it to be as low as possible.
Do you have any estimation when the temperature may go down to the initial temperature?
Well, I think like it's more visual. So it's like, as you can see in this bottom one, like it like equilibrates much faster.
Yes, I can see that, but eventually it should go down to the initial temperature, isn't it? Well, what if heat wave is longer than 2 days or 5 days? Would it change the model?
Oh yeah, we're assuming that the heat wave is gonna go for more than 5 days.
Oh, more than 5 days, you said?
Because like the outdoor temperature is directly from the heat wave like data.
Okay, all right, thank you.
Yeah, I have a question about your vulnerability score. Just want to ask if you could comment on why you decided that particular form, why multiply instead of maybe add or subtract?
Yeah, so while we were looking for parameters, if you want to go, yeah. So while we were looking for these parameters, we are trying to determine the relationship of each of them to the vulnerability, because most of these scores, if it's higher, then the vulnerability will go down, or if it's direct, then a higher dependency ratio means that it's going to be more vulnerable. And so with a bunch of inverse and direct relationships, that just naturally led us to think that, okay, maybe we can multiply some of them and then divide it by the ones that lower the vulnerability the higher they are, the inverse ones. And so that's what led us to the multiplication and division, although we did think about, we didn't really consider another formula for the vulnerability.
Okay. Just to follow up on that, so in terms of that form, one particular increase in the age of the structures has the same impact as an increase in temperature. I guess what's your reaction to that, and what might you do to try to make up for something like that?
Yeah, so while we were creating this, actually, we realized that a lot of the parameters had overlap. Like, for example, the percentage of adults with cars is almost certainly going to correspond with the average income in the neighborhood. And so we wanted to reduce it from the 20-something parameters that were given in the data sheet to as few as possible, and we probably could have gone further, but also we didn't especially want to reduce it to just 1 or 2 parameters because we felt like that would be an oversimplification. And so we just stuck with these 5, and then this last parameter also gave us an excuse to use our first model because we had that worked out, so we wanted to use it here.
And that's good, it's an important part. But just in terms of the impact, right? So what, a corresponding increase in age of structures versus corresponding increase in the temperature, why should that hit the same way?
Yeah, so we were actually trying to solve this in the challenge. We wanted to say like, maybe like income is twice as important as like dependency ratio, right? But that factor 2 just like goes away when you normalize. So next time we wanted to like maybe add, like if we did some addition instead, then it wouldn't go away when we normalized. So if we were to do this again, we would take things like that into account.
I think another thing is there may be other ways to add in weights, like you can use exponential factors, then that wouldn't go away in quite the same way. Because I agree, if you just did a linear weight, yeah. Can I ask a quick question about problem 2? So like for question 2, you had this nice curve where you plotted energy consumption versus temperature.
Oh, this one?
Yeah, what was the data? Can you just explain where the data came from? Like what were we fitting here?
So basically, we had energy usage for certain years, like let's say like I don't remember the exact time frame, but like 1990 to 2024.
Okay.
And then we also had the temperature, like the temperature for those years. So we just like fit them against each other.
So you sort of like you threw all the years into one plot, and then did a fit. Okay. Okay, that's all I wanted to ask. Okay, I think we're good then. Thanks, guys.
Thank you so much.
Thank you.
Yeah, if you want to thank anyone, you have a minute to do that now.
Okay, yeah. First of all, we'd like to thank our coaches, Dr. Teague, who's probably watching from North Carolina. Thank you so much for all your support. And also Dr. Levine and Dr. Tharp for coming on this trip with us. We'd also like to thank everyone who helped us come this far, our parents, our friends, and other math teachers as well. And yeah, last but not least, we'd like to thank our school, North Carolina School of Science and Math, for giving us this amazing opportunity to compete. Thanks so much.